Hey guys, we're going to be working on 8A.6. We're going to be going over the fundamental theorem of algebra. And without further ado, here we go. We want to find a polynomial with the given zeros, which means that when they solve for the polynomial, they got x equals 4, they got x equals 3i, and they got x equals negative 3i. Cool. If I move each one over to the other side, and I think we did this a little bit earlier in our videos, we get that. Let me change the second one. So now how do I get the factor, or how do I get a polynomial from these? Well, I put them all together in factored form. So I have x minus 4, that will be one of them. I'll have x minus 3i as another factor. And then lastly, I'll have x plus 3i. And we can call this f of x our polynomial. Now, we could multiply these out if we wanted to. We don't need to, though, but we could multiply these out. I'm going to multiply out these first two because I see that there is a conjugate here. So I only have to multiply the first term, which is x squared, and I need to multiply the last term, which is minus 9i squared. And if I simplify that, I get x squared plus 9. It does say find a polynomial, which means that my answer could have been at this point, or it could have been here if you expanded. Either way, it doesn't matter. We found the polynomial with those given zeros. This part, and it's in yellow here, will be coming up a little bit later. So pay attention to those plus and minus 3i's and plus and minus i's. Here's what the fundamental theorem of algebra says. If f is some degree polynomial, could be fifth, sixth, eighth, first, then f has at least one zero in the complex number system, provided that n has to be a positive number. Now, let's back up for a minute here. It says in the complex number system, so numbers in the complex number system are like 5i, they're like 3 minus 2i, they have an imaginary part, and they also have a real part. But you may be interested to know that the number 4 is also a complex number. And the reason I know that 4 is a complex number is because it has 4 plus 0i. So 4 in itself is a complex number. Now that we know that what a complex number system is, it's going to be all these numbers that are complex numbers, which are basically, again, reals and imaginaries. It says that a polynomial has at least one zero in the complex number system. Well, it's called the fundamental theorem of algebra, and I'm hoping that this makes sense. And here's why. If I have some polynomial, and feel free to draw this, feel free to not draw this. If I have some polynomial and I graph it and it looks like that, well, duh, it's going to have a complex root, because no matter where you draw that, no matter how you draw the polynomial, the graph will intersect the x-axis, or the graph will not intersect the x-axis. Where the graph intersects the x-axis will obviously be a real root, which is a complex number, or it could be an imaginary root, like this guy doesn't intersect the x-axis, but we learned in the last unit that if there's no x-intercept, that means that the quadratic has two complex roots, imaginary roots. My point is, it says that f has at least one zero in the complex number system if f is an nth degree polynomial, and that should make sense for us. So let's try a problem. We want to find all zeros and write the function complete factored form as a product of linear factors with f of x equals x squared plus 9. Well, this one is not going to be that bad. Like, you should have already solved this before I even finish, because this was an okay problem for us to deal with. Here's our zeros. So we got all the zeros. Put a purple box around that. And then for the factored form, as a product of linear factors, all that's asking us to do is to take our answer and do an x minus 3i and an x plus 3i. And it's linear because I have x to the first and x to the first. Those are my two answers. Hopefully you're not finding this too bad. I just want to go back here to fundamental theorem. So will our polynomial have at least one zero in the complex number system? This one did. It had two numbers in the complex number system. Here we want to find all zeros and write the function in completely factored form as a product of linear factors. I'm going to give you a hint before you go and start this on your own. Don't try to do anything that's fancy, like from the last section, if you can actually factor the polynomial right away. Hint, hint, you can factor this polynomial right away. Hint, 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 try grouping. Pause the video now. Okay, you probably unpaused the video by now, so let's see if we got the same thing. I am not doing rational zero theorem. I am not going to do anything fancy except for a good old factoring. I love factoring. Factoring is my friend. My only friend is... That's not true. So we have x squared plus 9 times x plus 1 are the factors. Now if I want to find the zeros, I said f of x equals 0. That means x squared plus 9 equals 0. X is equal to plus and minus 3i. And I gotta set x plus 1 equals 0. And x equals negative 1. Those are my zeros. It's all of them. Second, let's go ahead and put this in linear factors. That means I'm going to have x minus 3i. I'm going to have x plus 3i. And I'm going to have x plus 1. I could multiply this out if I wanted to. Don't really feel like it. Here we go. My two answers. Hopefully you got that correct, and hopefully it wasn't too bad. Please note, we have three numbers in the complex number system, which kind of came from this idea, the fundamental theorem. If you have a cubic degree polynomial, then f has at least one zero. For this problem, it's true as well. So here's an idea. Every polynomial could be written as a function with a product of linear factors. If you take a look at this one, linear, linear, linear. If you take a look at this guy, linear, linear. Every single polynomial that you can think of can always be rewritten as a polynomial with linear factors. Always. Now, in order to get that done, that's going to be a little bit of work. And please note that C1 and C2 and all these extra numbers here are going to be complex numbers. So there might be a real number here, there might be an imaginary number here. Cool. So we have our work cut out for us on this one. We have to do, given this polynomial, we have to list the possible rational zeros, which is from the last section. So you will need to do that P over Q thing. I'll give you a little note here. So we have to do P over Q. You want to find all the zeros. So this one, you'll want to use your calculator to double check, see where the roots actually happen, and then use synthetic division to reduce this quartic equation down to a quadratic. And then you want to list this in a linear factored form. Good luck. Pause the video now. Okay, so if you listed out the possible rational zeros, and I'll show you the answer in a second, you're going to get a lot of numbers. I think it's 4 numbers total. and then you're going to find the zeros using the calculator. So I actually graphed this just because I didn't feel like really doing a lot of the work. Just kidding, I did all the work. And I get this cool looking thing. And holy moly, guacamole, Batman. It looks like I got a root here at x equals 1, and I got a root at x equals negative a half. And if you did your rational zero theorem, where you did the p over q, I bet one of those rational zeros was probably going to be a positive 1 and probably going to be a negative a half. And if you thought that, and you did synthetic division on positive 1 for that polynomial, and you did synthetic division on negative a half for the cubic polynomial, then that means you were left with a quadratic, which you could solve. And let's see, my friend, if you got the answer. Bam! Possible rational zeros. There were 4 of them total, 4 rational values, 8 total with the negative. If I tried 1 on the synthetic division, I got 0. Now, you might have asked yourself at some point, how come when I did negative a half, I didn't go back to the original polynomial? If you get a remainder of 0, and I never said this in a video before, if you get a remainder of 0, you use that new polynomial to test another potential 0 of the polynomial. So I will not do synthetic division of negative a half on f of x. I'm going to do it on that cubic function. And if I did that correctly, I get 2x squared plus 8 equals 0. Move the 8 over to the other side, divide by 2, I get x squared equals negative 4, and I get plus and minus 2y. So all the zeros that were possible were x equals 1, x equals negative a half, and x equals plus and minus 2i. Please note, if it said find all the real zeros, you would ignore the imaginary parts, and you would just put the first 2 answers. And if you list it in factored form, you get that beautiful looking thing there. And if you really took the time to multiply it out, which you are not required to do, you should end up back with the original polynomial that we had. Here's another problem. Please pause the video now to try it on your own. All right, now I'm assuming that you already tried the problem on your own, and I sincerely, from the bottom of my heart, hope that you actually tried to factor this first. And you should always, my friend, try to factor first before you do any of that fancy stuff. And what do I mean when I say fancy stuff? That rational zero p over q thing, do not even try that with synthetic division using your graphing calculator, because that is way too much work. Here's what you get. Take out an x right away. X to the fourth plus 2x squared minus 3 is what's left over. Please notice that the degrees are even, and I get x to 0 at the end, which means this is a quadratic-like polynomial that can be factored into x squared plus 3 and x squared minus 1. Take f of x, set it equals 0. Please don't forget about this little x on the outside. Set that equals 0 for sure. That's 1, 0. Take each of those others, set those equals 0, and you get plus and minus I root 3. If you have plus and minus the square root of negative 3, that would be fine. And plus and minus 1. Hopefully you didn't have too much of a hard time with that one. That one was not supposed to be a problem that destroyed you. So what do you notice about the complex roots? Well, what we notice is that, for the sake of time, they're in pairs. If I have a positive 1, I get a negative 1 with the same thing. And if you go back a couple examples, a positive 2i, a negative 2i. Boom, evidence. A positive 3i and a negative 3i. They appear in pairs. There's a plus and a minus of the same number. That will come in handy for the next problem. Last one. Find a polynomial with real coefficients. Let's do x equals 2y. Let's do x equals 2. Let's change the color. X minus 2i is 1, x minus 2 is the other, but we need the positive 1 as well. We need x plus 2y equal to 0. And then finally, my answer is x minus 2i, x plus 2i, and x minus 2. They are real coefficients. Here's my answer. Thank you for watching.